These are passed, so I'll go through them quickly. I didn't screen them this morning to do, so I'll try to do as quickly as I can. I know you can tell them we'll do that for you today. Y'all seem like you're nice enough today. I'll do that. Okay, the scholarship opportunities at UAB and UA, presidential scholarship, that deadline passed. I think today's the deadline for the NCAS. That's NASA Community College Aerospace Science Program or something like that. That one is due in today. So if you're interested, I've got the flyer. Please get that accomplished. I think it's about 5 o'clock today. There is, this deadline is already passed. This is coming up, I think, tomorrow, okay? First call quality services out of Indianapolis, Indiana, will be at the One Stop Center tomorrow. That's in the Millsap building right next door to us here, just outside the loop. To the north here, to the north here, and they will be taking applications for the job fair. This is quality inspectors, $11 an hour, team leaders, $13.50 an hour. This will be tomorrow, March 6th, the One Stop Center right here in the Millsap building between 9 and 1. Benefits are available. It's not just contract work. They will provide some benefits. Applicants must have a clear background check, driver's license, high school diploma or GED, and automotive manufacturing experience is preferred, not required, but preferred. You can contact Ms. Brenda Thomas or Ms. Dorothy Henry, either one of those at the One Stop Center. Now, this is also stuff that you can spread among, I should have said this last week, people if they're looking for work, this might be something. If they've worked in the automotive industry, they would like an increase in pay maybe or something like that, they could show up. I mean, that's what they're here for, to spread the news around. Certainly it's for the Boston folks, but it's also for others as well. Ms. Gerasi is always interested in getting more people there for math team practice today at 3 and every Monday at 3. Birmingham West Campus, C100, it's the science building, C100, and also Friday noon, same place. She was at the meetings, same meetings I was at last Friday, but she'll be there this Friday, as far as I know. Tutoring schedule, I've announced to you before what they are on this campus and some on the Birmingham campus. Let me encourage you to consider tutoring. If you really want to learn math, try tutoring. When you have to explain something to somebody else, you really learn it well. So it's a great opportunity, but if you need help, you can also get help there. Okay? That meeting is over with, and that meeting was canceled, and any of you graduating this term? I
graduated in summer.
Oh, that's summer, okay. Well, actually, if you're participating are you walking?
Yeah.
Oh, you're not, okay. So you don't need to know this. If you know of anyone who is graduating, okay, there is a meeting this evening, Birmingham West Campus, the ACAT building, first floor theater. Tomorrow they're on this campus at 1:30 in the Ethel Hall Auditorium right across the parking lot from us here, 1:30. And then Wednesday on the Birmingham campus, ACAT Fit building, again at 1:30. So today is 6 o'clock on Birmingham, 1:30 tomorrow here, and 1:30 Wednesday on Birmingham. Okay? That pretty much wraps up the announcements. I was hoping others would come in, but they haven't yet, so let's go on and get started. Any questions on anything non-math related, school related, or anything calculus related? No questions? All right. So, where we left off last time, we were still on the chain rule. This is section 2.4, almost at the end of this, okay? And we're page 138, top of the page, trigonometric functions and the chain rule, okay? We did a lot of power rules and other things. Let's do trig functions with the chain rule. All right. The chain rule versions, they put in quotes, of derivatives of 6 trigonometric functions are as follows, okay? If you're taking the derivative of the sine of u, where u may be a function itself, okay? Then, of course, you do the derivative of the outer function, derivative of sine is cosine of u, and then if u is also a function of x, then you have du dx, or what they call u prime. Same thing with cosine. If the u is a function of x, then the derivative of cosine is minus sine u, same variable there, and then you take the derivative of u with respect to x, u prime. Tangent, just as before, derivative of tangent function is secant squared, and then if u is a function of x, then you do derivative of u with respect to x, or u prime. Cotangent, very similar, except it's minus cosecant squared u times u prime, and derivative of secant u would be secant u tangent u. That's the derivative of the secant. Then the chain rule then turns around and takes the derivative of the innermost function u prime. Cosecant minus cosecant u cotangent u, then u prime. Now, I don't recall if when we did science the trig functions before, if they laid them out in this way, but this is how I try to remember them, but I don't try to memorize these things. If I need to, I'll look them up. But, if you do them often enough and frequently enough, you usually get so you know them. But notice the function, the pure function, sine function, tangent function, secant function, those derivatives are the positives. Derivative of sine is cosine, derivative of tangent is secant squared, derivative of secant is secant tangent. Okay? But then the cofunctions of those, cosine, cotangent, and cosecant, the derivatives are all negative. It just happens to be that way, so it's a sort of a helpful, maybe mnemonic device to remember where to put those minus signs, okay? But it's the same type deal. Derivative of sine is cosine, derivative of cosine is minus sine. Derivative of tangent is secant squared, derivative of cotangent is minus cosecant squared. Derivative of secant is secant tangent, derivative of cosecant would be minus cosecant cotangent. So, just another little pattern that probably has potential to be helpful anyway. So let's see what examples they show here. First, they show example 10, so let's go with it. And why in the world they do all the work for you, I'm not sure. I want to just do this. Okay. If y is equal to sine 2x, what would y prime be? And y prime would be dy dx, by the way. What would that be?
Cosine 2x.
Cosine 2x, there's the first part.
Say times 2.
Times 2, exactly. Derivative of 2x then would be 2, so then you move that up front to cosine 2x. Now, you will begin seeing this sort of often enough that a lot of times people will do the u prime first, because that's going to wind up being written first, okay? And there's nothing wrong with doing that, but just remember, you have to take the derivative of the outer function and then the derivative of the inner function. So whichever order you do it, it doesn't matter, but just don't forget to do both of them, okay? Let's go to the B part here. What you got there? Y prime would be?
Negative sine times x minus 1.
Yes, exactly. Times?
1.
1. So that's nothing. You had it right there. Minus sine of x minus 1. And we have Terrell right here. Okay. All right, got it. Okay. We're doing the trig functions with the chain rule. Okay. We just finished 10b. Let's do 10c. Here we have y is equal to tangent 3x. What would y prime be then?
Secant squared.
Secant squared
3x.
of 3x times
3.
3. Exactly. And then you can move the 3 up front. And I guess you might ask, why do you typically put the 3's in front or the 2 in front? Well, if you left the 2 here without all the parentheses there, you might ask yourself, was that 4x in? No, that's not what it, or is that 2 supposed to be a superscript, like sine of 2x squared? No, it just removes ambiguity to move it in front. It's 2 times and 3 times. Because leaving it at the end, it just gets a little confusing. You don't know if that's part of the argument of the secant squared or the cosine. It's not. It's a multiplier, so typically move it out front. That's example 10. Any questions on those? Pretty straightforward. Notice B had no change at all because the root of x is 1. Okay. Now, they're skipping examples. And, oh my, I think I've recognized him. I've seen you somewhere before, haven't I? Yeah, I thought so. Jeremy's here. All right. Okay. We are doing differentiation, chapter 2, trigonometric functions in the chain rule, and we're just getting started on example 11 on page 138. However, it's not on the slide set, so I'm going to do it on this page. Let me get my pen set up. Okay. All right. Here is their A, 11A. Y is equal to cosine 3x squared. Okay? Now, what we're looking for is y prime. Now, I don't know why they're making sort of a big deal about it. Is there any ambiguity here of what is being used, what the innermost function is? It doesn't look like there'll be a problem with me, but is there with you? When you look at this, do you know what they're really asking for? Yeah. The book, this author, I guess, makes a big deal about if there is ambiguity, put this in parentheses. Okay? And now it should make more sense to you, but to me it doesn't add much. But then on the other hand, if you're doing anything on your calculator and you have a trig function there, guess what? As soon as you put the cosine function there, most of the time they're going to open that parentheses for you. So you're probably used to seeing it with the parentheses there anyway. So anyway, you tell me what y prime would be. Whether you put the parentheses there or not, what would it be?
Negative sine 3x squared.
Perfect.
Times 6x.
Times 6x. And a lot of times we will choose to write it just so you don't get it confused and think somehow that's part of your argument. It's not. That's separate. So bring the 6x up front. 6x times, or minus 6x times the sine of 3x squared. Okay? And then you can put this in parentheses or not. I don't care. Okay? In the book, they leave the parentheses off. Does that make sense? Is there any ambiguity there, or does it make... It seems like that's what it should be. Feels good to me, but I'm used to this stuff. Now, how about this one? y is equal to the cosine of 3 x squared. I think I see what they're doing now. Okay, what is that y prime? Now, frankly, I've never seen a problem like this, but you could. I mean, it's a legitimate problem. But what does that mean?
Well, I'm looking at the book here, and I had the wrong stuff, but negative sine 3.
Okay, now here's the deal. 3 is a number, right? A constant. Now, if you see cosine 3 or any trig function followed by a 3, what do you assume right then? You're in what mode? Radians. The only way that could be degree if it had a degree symbol by it. If you don't see a symbol, that's 3 radians. Well, cosine of 3 radians, or cosine of 3 degrees, is just a number. And it's the coefficient of x squared. So this would be like 17 x squared. Or whatever, 0.35 x squared. It's just a number. 3 is just a number in radians, and cosine of some number of radians is some other number, between negative 1 and 1, of course, because cosine is always equal to that. So that's just a coefficient for x squared. So what is your answer? What's the y prime here?
Cosine 3 times 2x.
Yes, which I'm going to write is 2 times cosine 3. Now this one, be sure you put in parentheses x. If you do not put that one in parentheses, then you are going to think that answer is cosine 3x. So you've got to put that in parentheses. So that's what the point is. That first one was just arbitrary whether you put the parentheses or not. This one, it's got to be there. Okay? And that's what they got. Good for them. Wait a minute. Oh, I see. Yeah. The other way you could have written this, I didn't think about this, is 2x cosine 3. There you don't need parentheses because it's obvious that cosine 3 is just a number. But because it's just a number, I tend to put it with the coefficient because that's where it belongs. But it is perfectly okay to write it that way. All right. Number C, or letter C. Y is equal to cosine 3x squared. Okay, what's your y prime here? Any ideas?
Negative sine.
Okay, you certainly are going to start that way. Negative sine of okay. It's okay to do that. I'm going to write it the same way they did. 3x squared. Because that's what you're doing. You're just taking the derivative of cosine first, the outer function first, and that's negative. Now, you're absolutely right, or you're awfully close to it, but you still have some part of the chain rule yet to go. And what's that? Times. Huh? Okay. Yeah. That is correct. It's Nakoma, right? Okay. Try to get you on the right line here. Okay. Now, I kind of like the way you're doing this, but I'm going to do it the way I think they're doing it. Okay? Not sure. It's 2 times 3x, right? Okay? But then you still have another chain rule to go, right? Times Derivative of the inner function there is 3. Okay? Now this is really the long drawn out way to do it, which would then make it, let's do the minus first, and 9 times 2 is minus 18x sine 3x squared. Okay? Now, you could have made life a whole lot easier if you had done this. Now, this is what I thought you were getting at to begin with, and maybe it was. Let's rewrite this as y is equal to cosine of, let's square that to begin with. What would that give you? 9x squared, right? Now it makes it so much easier to do your y prime would then be minus sine of 9x squared. I'm putting it in parentheses now just so you'll see it, times, what's the root of 9x squared? 18x. So this would give you minus 18x times the sine of 9x squared, which is minus 18x times the sine of, and if you square 3x, you get 9x squared. Okay, so I think it's far easier to do it that way. I don't know if this is what they intended, but you have the outer functions of cosine, that's derivatives minus sine of the same thing you had inside. Then the next inner function, which is itself an outer function, is 2 times 3x, and then the inner function, the derivative of that is 3. Okay? It gives you the same answer, but so much easier if you just take this thing and square it to begin with, make it 9x squared, and then just do that. Okay? You eliminate an inner step there, okay? And you get the same answer with, I think, a lot less ambiguity. Okay? Oh, and that's actually how they did it, okay? I thought they were going to do it the other way, but you've seen it both ways now. So whichever way you choose, they went on and wrote that as 9x squared. All right, now here's another one. Here's your y is equal to cosine squared x. Now, what is your inner and outer function here? Cosine x is the inner function, and your power function is the outer function. Okay? So what would this be? Y prime would be 2 times cosine x, that's your power function, times negative sine x. You got it. Okay? So this would then be negative 2. I like to write sine x, cosine x. It really doesn't matter. I just usually think of sines first, and okay? How do they put it? They left cosine x, sine x. It doesn't matter how you do that, okay? So yeah, that's your y prime there. Make sense? Let's get this last one in. Here's y is equal to the square root of cosine x. Okay, I think you've been probably around me long enough to know what I would do next.
Get rid of the radical.
Yes, and how, yeah, rewrite it to get rid of the radical, and what would that give you?
Cosine of 1/2.
Yes, cosine to the 1/2 of x. Okay, now, both this one and this one we could have rewritten this way. I'll do it for that one. Cosine x squared. That makes it look like, yeah, for sure, the squaring function is the outer function. Okay? And if you wanted to, you could do the same thing here. Cosine x in parentheses to the 1/2 power. Don't give you the same thing. but that's the more common way of writing it. And what would be your derivative then? Y prime. One half cosine of what? You got to deal with the power first, right?
Oh, yeah, that's right. So the
negative one half of x times negative sine x. Okay? Now, if you put numerators where numerators belong, denominators where denominators belong, this is going to be a minus. I'm going to lead with that. In the numerator, you just have sine x. In the denominator, you have a 2 times the square root of cosine x. Now, I just did it that way because they gave you the original problem in radical form. I'm going to go back and put it in. See, cosine to the minus 1/2 is 1 over cosine to the 1/2, and cosine to the 1/2 is cosine. You don't have to do that. I'm perfectly happy you leaving it negative sine x over 2 times cosine x to the 1/2 power, or cosine to the 1/2 x. That would be perfectly fine too, but if they gave you radicals to begin with, put it back in radicals. The only kind of maybe a little bit of a disadvantage in writing it, leaving it in power notation, if you had a cosine to the 1/2 x down here, you might somehow think that's the tangent. It's not. If this is sine to the first and that's cosine to the 1/2, yeah, you can't get a tangent out of that. Unless you do tangent to the 1/2, the square root of tangent, times the square root of sine. But that gets just really complicated. Okay?
Why does sine go on top like that?
Okay? Because the derivative of cosine, your chain rule, is sine. It's no longer, the power here is no longer part of the picture. The inner function is cosine, the derivative of cosine is minus sine. And that's the numerator minus sine, not a denominator. The only reason that goes to the denominator is because the exponent went negative. But the derivative of cosine is still sine. And that's positive exponent sine. Okay. Okay? Makes sense. Good question, though. All right. That finishes example 11. They're also doing skipping example 12. So let's clear the slide and let's us do example 12. And we actually already did one kind of like this because we did it not the way the book did it. Let's do this one. F of t, you don't have to always have a y there, is equal to, and you don't always have to have an x there. This is sine cubed of 4t. Okay. What we're looking for is what in the world your f prime is. Okay? What would you do first?
Rewrite it with the exponent outside. I like that.
Say that again.
I'm just saying rewrite it with the exponent outside.
Okay, you certainly can do that. That's a legal move in most states. So you can do this as a sine of 4t cubed. Now, I probably put extra things in there, but just so you'll see that. Okay? And this, writing it that way, makes the outer, inner, and inner more obvious, I think. So what do you do first? Second? Okay, and what would be your first step in the chain rule? Yeah, 3 in front of the sign. You do the power function first. It's the outermost function. So that would be 3. I'm going to keep the bracket there, I think. I think you said it. Sine of 4t squared. Exactly. that's the outermost function, times say again? Yeah, you do the derivative of sine of 4t. That's your inner function now. And what's that? Derivative of sine is? Cosine of 4t. Okay. But even that has an inner function, which is 4t. And what's the root of a 4t? 4. All right. Now that's stringing it out, okay, to the max. Now if you group things together, you have a constant 3 here and a constant 4 there, and they're all multiplied, so that gives you a 12. And then it really doesn't matter the order, but just to keep things maybe a little cleaner, that was going to be times the cosine of 4t times the sine squared of 4t. Okay. I don't know if that's any cleaner or whatever than the other. If you wanted to put a bracket here, you can. It doesn't matter. That's sort of just extra writing that you didn't really need. But there's your answer. Now, there's nothing wrong with having 12 times sine squared 4t times cosine 4t. But make sure you have them obviously separated from each other. Okay? See how the book left it? They did 12 sine squared 4t times cosine of 4t. Yeah. And they left off the brackets, period, and didn't even put parentheses around 4t, which is fine. You really don't need it. It's pretty obvious that's what it is. But doing it this way, you see those functions as their entities. Okay? Not necessarily to have those grouping symbols in there unless it helps you see it better. If it helps you see it better, it's worth it. But if you understand what it is without them there, you don't have to have the grouping symbols at all. All right, good deal. But we still have one more example they skipped. Isn't it funny how they skipped the hard ones? Okay, well, not hard ones, the more involved ones. Okay? So let's erase all that ink and go with example 13. This time it says, find an equation of the tangent line to the graph of, so we're looking for find equation of tangent line of this function is equal to 2 times the sine x plus cosine 2x. Okay? At the point pi 1. Okay? As shown in the figure. Okay? Time out. Okay? As you probably have sensed by now, I'm somewhat of a cynic. Okay? And when I see something like this, the first thing I'm going to do is plug in pi for x and make sure the f is 1. Because if you don't, if it's not, that point's not on the curve, you can do a lot of wasted effort and find out it makes no sense. Okay? So let's do it first. So plug in the pi here. So alpha pi, that's your x value, is equal to 2 times sine of pi. What's the sine of pi? 0. Sine, remember, starts at 0, is 1 at pi halves, and then it's 0 again at pi. So that part is 0. Okay? Cosine of 2 times pi. What's cosine of 2 pi? 1. Yes, that one is 1. So sure enough, this is 2 times 0 plus 1. That's going to be 1. Yes, they gave us a problem that made sense. Okay, there is a term for that. What do they call that? Well-posed problem. Okay, they gave you something that does make sense. That is the point on that graph. Okay, so how are we going to find an equation of the tangent line of that function? What are we going to need to know the equation of a line? Yes, all right, it's a good choice. And Cal 1 class is take a derivative. And by the way, I said this at the meeting. I gave this as an example. Okay, f prime of x. And what is it, by the way? Okay, I hear some little mumbling, but I can't make it out. 2. A little louder.
2
cosine x plus, or maybe not,
plus negative.
Okay, so I'm going to put minus sine 2x Did you chain rule it?
Oh, yeah, so it's got to be times 2.
Okay, sine 2x times 2. So I wrote it as 2 cosine x minus 2 sine 2x. Believe we got it right now. Okay. Now, why did you take a derivative in the first place?
So you can figure out your slope.
The slope, exactly. That's what the derivative will give you. And where do we want that slope? At pi, when x equals pi. So f prime of pi is going to be, I'm going to go on and factor out my 2's, and then let's just plug in, what's cosine of pi? Is it? Yeah. Say again? Okay, we've got 2, multiple choice here, huh? -1, okay? Remember, cosine starts at 1, at pi halves at 0, and at pi it's -1, okay? I tend to think in terms of graphs, okay? Of sines and cosines anyway, okay? So that's -1 minus 2 times the sine of what? Okay, but it's not pi. Yeah, it's 2 times pi. What's sine of 2 pi? At 0. So forget that. Okay? So what we have here, your first derivative at pi is -2. Done. Got it. Okay? All right? And you just told me that gave us a slope at that point. So how do we go from here?
I need to fill out a unit circle again.
What's that?
So I think I need to fill out a unit circle again.
Oh, yeah, well, maybe for what we're just doing. But from what we're doing right now, what do you do? You're looking for an equation of a line. Happens to be the tangent line, and we set up everything for that. What do we need to get an equation for a line? Okay, we got the slope. And what else do we have? Second.
Y equals mx plus b.
Okay. Now you actually could use that, but but it's going to be a little, you could use it. But the formula actually will be a little easier for you. That's called the slope-intercept formula. But what do we have here? We have the slope, say again? Point slope. There's a point and there's a slope. And how does that point slope formula go? Y minus y1 is equal to m times x minus x1. That's it exactly. Where y is the variable y. No, that's the variable y. The y1 is, that's the number 1 from right there. Exactly. Is equal to what? -2. That's why we did the derivative in the first place at that point. Times, what's the x? It's the variable x. Leave it alone. Minus pi. That's it, folks. But we can clean it up a little bit. That'll be y minus 1 is equal to -2x plus 2 pi. Okay? And then add 1 to both sides, and that gives us y is equal to minus 2x plus, I don't care which order you do it, 2 pi plus 1, or 1 plus 2 pi, I don't care. Okay? In fact, that may not even be the best form. Maybe just leave, I think that is the best form. I always like the slope-intercept form. The intercept here is 2 pi plus 1. Now, 2 pi is approximately 6.28, so that'll be 7.28. So the y-intercept is going to be way up here at 7.28 or 7.25, somewhere around there, okay, and the slope is going to be -2. There it is. And if you look at the figure in the book, and this is one thing that sort of gripes me, I tend to like Larson's text. I don't really like Cengage, the publisher, but I like his text. But one thing he said is they've done for this calculus text is not put in the figures. And if I'm teaching that, I have to refer you to the book for the figures. If you don't have the book, then you don't know what we're talking about. I wish they'd go on and put the figure on here too. But you see there is the curve. Thank you very much for graphing it for me. I didn't want to graph it. And you see the point pi 1, pi being 3.14, somewhere out there, that's to the right, go up 1. You see the tangent line there, and sure enough, that looks pretty close to a -2 slope. And you see if you extended this on upward to your y-axis, you would have to go up quite a ways, and for it to be 7.25, 7.28, whatever. Yeah, that's going to be pretty close. So everything looks like it's okay on that. Okay. So that was the first part of the problem. Find an equation of the tangent line to the graph of f of x equal 2 sine x plus cosine 2x at the point x1, as shown in the figure. Then determine all the values of x on the interval 0 to 2 pi at which the graph of f has a horizontal tangent. That's usually what we're a bit more interested in. So this time, I'm going to erase part of this. This probably will be more pain in the neck than it's worth, but let me just erase part of it. It may not be my neck either, but never mind. Okay. All right. And we'll find, well, we're finding something. Well, I did, okay. I'm going to leave the function alone. Well, I erased way too much. Oh, I probably could have used that, but I already erased it. I should have just erased everything. But I left the function. I got carried away. All right. Then determine all the values of x such that x in the interval from 0 to 2 pi, at which the graph of f of x has a horizontal tangent. Okay. Now, how's another way of saying that? Places where f of x has a horizontal tangent. That's wordy. That's written in English speak, which is sort of long and awkward. How would be an easier way to say that? Where f prime of y, f prime of x, if these are x's, they are, aren't they? Yeah. Where f prime of x equals 0. That says it's a horizontal tangent. It says it has 0 slope. It's horizontal. The tangent is horizontal. So that's a much easier way of saying it. Now what I regret is that I erased my f prime, but it's not too hard to do again, is it? What was this? 2 cosine x minus 2 sine 2x, right? And we want to set that equal to 0. Okay? Now the first thing I'm going to do, what would be the first thing you would do? No, you don't plug in 0. That's not what it's asking. It's asking where the f prime is equal to 0, not where f prime of 0. That's different. What's that? Okay, you could start plugging in. That's one way to do it, but it's not the easy way. Easy way is just
Subtract 2 cosine x.
Okay. Now that might be a possibility. I'm not sure that's all that easy either. One of the first things I'm going to do is factor out a 2. Okay? In other words, I'm going to divide out a 2. Divide 2 here, 2 there, and 2 will go into 0, 0 times. Okay? So I got rid of those. Now, it may be that your best bet is to, this one is a little more. Okay. I'm going to, I want to get that sine 2x in terms of some trig function of x alone. In other words, not 2x, but x. Does anyone remember that identity? Sine of 2x is, I take it, not. Okay? Let me back off one more time and say, does anyone remember this identity? Okay? Sine of alpha plus beta, or a plus b, I don't care. Anyone remember that one? I'll lead it off. Sine alpha cosine beta plus, I'm going to write it this way, sine beta cosine alpha. Y'all don't remember that, I take it, right? Okay. That was the sum angle formula. If you're taking the sine of the sum of two angles, it's the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. I don't care which way you write it. But what I'm getting at is, what if alpha and beta are the same? In other words, beta is equal to alpha, alpha is equal to beta. Then that would be sine of alpha plus alpha, right? If beta is equal to alpha, that would be that. And that would be what? Sine alpha cosine alpha, if alpha is equal to beta, plus sine alpha cosine alpha. That's why I wrote the sign first. Well, what is alpha plus alpha? I think we can do that, can't we? Sine of 2 alpha, right, is equal to 2 times the sine of alpha times the cosine of alpha, right? Okay? Now, diamonds here. Here you are. All right. Group in the middle of the alphabet is doing quite well. The extremes are a little on the short side. Okay? All right. And we brought in the lower part of the alphabet as well. Okay? Now, so sine of 2x would be, since sine of 2 alpha is 2 sine alpha cosine alpha, what would be sine of 2x? Yes, 2 sine x cosine x. And that's equal to 0, right? Now, what can we do? Cancel like terms? Why do you want to cancel that? You like to get rid of things, don't you? You're not a hoarder. You just throw things away. No. Okay? When you have, this isn't, say again? Okay. Now, if this were an earlier class, I don't know if I've told this one to this class, but some of you have been in my earlier classes, better remember this. What's the F word? Better, huh? Factor, exactly. Can't we factor something here? Yes, let's factor out a cosine x, greatest common factor, and what does that leave us? 1 minus 2 sine x. And that's equal to 0. Hey! Think we can do something here, can't we? Or can we? Set each of them equals 0, is that what I heard? Okay. That means either cosine x is equal to 0 or 1 minus 2 sine x is equal to 0. Okay? How about that first one? Now remember, we're in between 0 and 2 pi. Where between 0 and 2 pi is cosine x equal 0? Cosine 1? I didn't remember that identity. Where is cosine 0? Okay, again, I think in terms of graphs. And we're going from 0 to 2 pi. So let's do pi halves, pi, 3 halves, pi, 2 pi. Okay, cosine starts at 1, has a 0 there, then go down to minus 1, then up to 0, and then up to 1 again, right? So where is cosine 0? Pi halves and 3 halves pi. So this x is equal to pi halves or 3 halves pi. Okay? All right, on the second one, what can we do? Say again? What you're wanting to do is solve for x, right? So what do we do?
Minus 1.
Okay, you can subtract 1 from both sides of that equation if you wanted to. That gives you minus 2 sine x is equal to minus 1. Now what? Say again? Add. Did you add 2? I don't think so. How is 2 related to sine x here? I don't see a minus sign, a plus sign in there. With no sign in there, that's multiply. How do you undo multiplication? Divide. Let's divide by what? Second? -2, I like it. Okay? And that's going to give us sine x is equal to 1/2. Now, where in between 0 and 2 pi is sine equal to 1/2? And again, I like to draw a little graph here. Okay? So I'm going to erase this one, if I can. Okay, and I'm going to put a sign in there. Okay, where does sine begin? 0 goes up to 1 at pi halves, right? Then down to 0 at pi, down to -1 at 3/2 pi, and then up to 0 at 2 pi. Right? But what we're interested in is 1/2. So where does this graph, ooh, that's ugly, equal to 1/2? Here and here. Does anyone remember what angle you take the sine of it, do you get 1/2? That's what we're looking for. Say again?
Is it a quarter? And
Okay, a quarter, like 25 cents?
no, like pi quarter.
Oh, pi fourths, right? I thought the sine of pi fourths was 2/2.
Just can't remember.
Huh?
Just can't remember it.
Pi 6. You're absolutely right. So it's at pi 6. Mine doesn't look like it, but it would be pi 6. So this would be x equal pi 6. And then one more over here. 5 pi 6. Okay. So here are your solutions. X equal, I'll put them in order, pi 6, pi halves, five pi 6, yeah, and 3/2 pi. Okay, I think I got them all. Those are the 4 places where your tangent lines are horizontal. Okay. Now, let me go back to unit circle. I think you were wanting to take me there a little while ago, right? Let's go to that unit circle. Okay? Here's a little trick. This is how it helps me remember. Here, your angle is 0. Your theta, your x is 0. And there, your sine is the square root of 0 over 2. And the square root of 0 is 0, 0 over 2 is 0. Okay? When you go up to pi 6, it's the square root of 1 over 2. Well, what's the square root of 1? 1. So 1/2. So the sine is 1/2 there. When you go to pi fourths, that's exactly bisecting that, you're at square root of 2 over 2. And when you go to pi thirds, okay, somewhere up here, you're at square root of 3 over 2. And when you get to pi halves, you're at square root of 4 over 2, which is square root of 4 is 2. 2 over 2 is 1. So the sine of that is 1. So that's how I remember it. Our favorite little lines, 0, pi 6, pi 4, pi thirds, and pi halves. Okay, those are the ones we remembered, right? It's square root of 0 over 1, which over 2, which is 0. Square root of 1 over 2, which is 1/2. Square root of 2 over 2, that's your pi quarters there. And this one would be square root of 3 over 2, which is exactly what that is. And then square root of 4 over 2 is 2 over 2 is 1. So that's a little mnemonic device that helps me keep those straight. Okay? And those are our angles. Let's see if that made it look like it made sense. And I wish they showed the graph. Now I feel like I've got to graph it. Yeah. So let me erase some of this if I can. And I'm going to take their graph. I'm not going to graph it from scratch. But I'm going to copy their graph. Hope they got theirs right. Okay? I think I probably can make that assumption pretty easily since they've just used it twice. And we haven't found any error with it yet. I'm going to leave the function there because I need. Okay. All right. Let's see what that graph looks like. Okay. When x equals 0, sine is 0, and cosine is 1. So here we have a 1. Okay? And that's where we are there. We're only interested from 0 to 2 pi. So let's just go and line that up. Let's make this 2 pi. Make this pi. Make this pi halves. Make this 3 halves pi. Okay, my scale probably isn't very good, but you live with it, okay? Now, this is increasing from here, and it goes up to some value, I'm guessing about 1.4, but I don't know that for sure. Okay, and so it goes up here, seems to come down here, back up here, looks like a big molar tooth, okay? And then goes down here, and reaches a minimum somewhere down there. It looks like about -3, so I probably didn't go nearly far enough. Okay, and then goes back up. No, goes back up. It's a periodic, so it goes back up there. Well, it has a zero derivative there, there, there. Oh, and there. Okay. There we go. Okay. Yeah. Zero derivatives at 3 places. Pi 6. Pi half, I've got my hump too far over. It should be back this way a little bit. Pi 6. Pi halves 5, 6 pi. And down here, 3 halves pi. This should be much deeper. I just didn't allow that for it. So I was just copying the one they had. You're going to have another one then. Pi 6 away from here, but that's outside our area. So yeah, 4 places. First derivative is horizontal. I mean, the tangent line is horizontal. Okay, good deal. Now, finally, we're at the end of, well, let's get the end of this. The end of the section here, summary of differentiation rules. Oh, man. General differentiation rules. C is a real number. N is a rational number. U and V be differentiable functions of X. F be a differential function of U. Okay? Well, the constant rule. Derivative of a constant, any real number whatsoever, 4,585 thirds, okay? That is going to be, the derivative of that is going to be 0, because that's just a constant, okay? Cosine 3, just a constant. The derivative of cosine 3 is 0, because it's just a constant, okay? So the derivative of the constant is 0. Simple power rule. Now remember, this n can be any rational number. It doesn't have to be an integer. Any rational number, d by dx of, of x to the n is n times x to the n minus 1. Now if n is a rational number, that'd be 5 thirds, and subtract 1 from it, and you get 2 thirds, okay? So that's just a rational number. And why they didn't put this one in place first, I would put it over here, d by dx of x is just 1, because the coefficient is 1, the exponent is 1, 1 times 1 is 1, drop the exponent by 1, that makes the x to the 0, x to the 0 is 1, so everything's 1, okay? So the derivative of x is 1. Derivative by x to some power is the power times the x to the n minus constant multiple rule. If you just have a constant times some function of x, pull out the constant c times the derivative of u with respect to x, which I just call u prime. You sum in your difference rules, d by dx, like saying that, of u plus or minus v, if both of these are functions of x, would be u prime plus or minus v prime. You just take the derivative of a sum or a difference is the sum or the difference of the derivatives. Product rule, can't do the same thing, but it's not similar, it's a different rule. D by dx of u times v is u v prime plus v u prime. Okay? First times derivative of the second plus the second times derivative of the first. The order doesn't matter, okay? Because multiplication is commutative and addition is commutative. So it really doesn't matter. The quotient rule of the order matters, okay? Because now we're dealing with quotients and differences. D by dx of u divided by v, where u is a function of x and v is a function of x. This is the other little line, kinda. Low d high, v times u prime, minus high d low, u times v prime, over low, v squared. Okay? Now, the chain rule. If you have derivative of a function of another function, take the outer derivative first, it doesn't matter what order, outer derivative, f prime, at the inner part, u, but then take the derivative of u prime, derivative of the inner part. Now here's a general power rule as opposed to the simple power rule. Now we're taking the derivative not of x raised to the n, but u raised to the n. Well, n times u to the n minus 1, that does the same thing. Then you do the chain rule on it and do u prime. So that's also part of the chain rule. Then your derivative of your trig functions, d of sine x is cosine x, derivative of tangent x is secant squared, derivative of secant is secant tangent. And then the cofunctions, same type deal, the only thing is they're all negative. Derivative of cosine is negative sine, derivative of cotangent is negative cosecant squared, derivative of cosecant is negative cosecant cotangent. Very simple. And if these were used here rather than x's, then it would be the same thing, or it would be cosine u, u prime. Negative sine u, u prime. Same thing there. You just take the chain rule of that inner function. All right, any questions on that? Okay, that's the end of the section. Let's take a look. Now, this book's concept check, back, same author when he did the pre-calculus book, he had a little single answer or matching or various things like this. This one, he just says, describe the chain rule, describe the general power rule. Do those in your head, okay? So homework exercises here, any of the odds, 3 through 7, all those odds are at calcchat.com, 3 is at calcview. Do any of the odds 9 through 33, a whole passel and a half of them there. All those odds are at calcchat, 9 is at calcview. Do any of the odds 35 to 53, they're all at calcchat, 37 is at calcview. Do any of the odds 55 to 59, they're all at calcchat, none of those are on calcview. Do 61s, the only one like that, we did one kind of like it in class, so do 61. Another one, but not quite right, we probably did one like this in class too, but if we didn't, we'd still do it. Excuse me. Any of the odds 63 through 69. My eyes are stinging like crazy. They're all at calcchat, none of those are at calcview. Okay? Then do some of the odds 71 to 77, they're all at calcchat, the 75 is at calcview. Then they do some famous curves, okay? 79, do 79 is famous, this is half a circle, okay? do 81. Excuse me. Pretty good problem there, horizontal tangent line. Then do any of the odds 83 to 87. They're all at Calc Chat. None of them are at Calc View. Then do either 89 or 91. They're at Calc Chat, not at Calc View. And then 93 is sort of an exploring concept. So try to do that one if you can. And then try to do 95. 97 is a think about it type problem, so you can think on that. 99, I hope that's a Calc Chat also. 99, finding a derivative graphically, so you could take a look at that. That's probably done on Calc Chat. The Doppler effect, which is a pretty interesting physical phenomena, that's number 101. I would say from here on, do any of the odds 101 through 109. Those are sort of applied problems, and I would say pick the ones closest to your field of study or your interest or whatever, okay? Then there's a think about it on 111, 113. So do one or either or both of those. Do either, all right, 115 or 117, they both should be at Calc Chat, not at Calc View. Do 119 is another problem somewhat similar. Well, it's a little different kind of problem. And then they have some true false, 121 and 123. I assume those are both at Calc Chat, but if they're not, see if you can just think through. Now, what the Putnam exam challenge is, I don't know if 125 is at Calc Chat, but you could take a look at it and see. Okay. I would say if you're doing math team type thing, those Putnam challenges might be pretty interesting. Okay. I don't know if the math team questions or anything like those, but I would think that might be where you would find it. So there we are at the end of the section. Let's discard of my chicken scratch. I'll still record it, but I'm just not. Let's move on to 2.5. Now, how are we doing? Oh, yeah, we got about 30 minutes. No, 25 minutes. Okay. Let's see where we can go in differentiation. Okay, we'll do this from the current slide. Well, differentiation, we've done the general rules, you know, power rules, the sums and quotients and products and differences. We did the chain rule. Now we're going to do a concept called implicit differentiation. Okay? These are equations that your variables are kind of mixed up within each other, and you can't really separate the y from the x's, and so therefore it's hard to set it up that way and then take the derivatives. So what we do is something called implicit differentiation. Okay? So our objectives here are distinguish between functions where written in implicit form and explicit form. And we'll use the implicit differentiation to find the derivative of the functions you can't separate explicitly. So let's take a look at what we mean by implicit and explicit functions. Most functions, I'm not sure I agree with this, but most functions that we've been talking about have been expressed in explicit form. I agree with that. Most functions that we've dealt with so far have been explicit. Here's an equation. Y is equal to 3x squared minus 5. Here, y is written explicitly as a function of x. Variable y explicitly written as a function of x. Y by itself. You can isolate the y, the x is above itself. Some functions, however, are only implied in an equation. Okay? This would be explicit. Y is equal to 1 over x. That's explicit. However, if we have this equation, x times y is equal to 1, that is an implicit form. You can still write it explicitly by dividing both sides by x, and you get back to that, but this is written implicitly. In other words, you don't have in this form y by itself. It's multiplied by x, and its product is equal to 1. Okay? So, some implicit forms you can solve explicitly, like that one. Others you can't, or it's hard to do. Now, to find dy dx, d by dx of y for that equation, you can write y explicitly as a function of x and then differentiate. Okay? So that's what we were used to doing. Divide both sides by x. Y is equal to 1 over x. That's x to the minus 1. And what's its derivative?
-1.
Negative 1.
Oh, x to the -2.
X to the minus 2, which is negative 1 over x squared. You can do that anytime that you can solve for y. If you can write it explicitly, you can do that. You cannot, however, use that procedure when you are unable to solve for y as a function of x. Okay? So, for instance, this one. How would you find dy dx for this equation? X squared minus 2y cubed plus 4y is equal to 2. Can you solve that explicitly for y? No. Good luck with trying. You could try as subtracting x squared from both sides and factor out a y, but then you still have a 2y squared plus 4 that you can't solve explicitly for y. Okay? Well, that equation is difficult to express y as a function of x explicitly. I'm not going to say you can't possibly do it, but it sure is a lot of work. So it's much easier to use implicit differentiation. Now, I want to just go on and show you how to do that. Okay? Though I'm breaking from protocol in the book. Okay? But here's what you do. It's kind of a use of the chain rule. Okay? So if we start taking a derivative of this thing, okay? In other words, we're going to do d by dx of this and d by dx of that. Okay? Now that looks like a sum and a difference. Let's start doing it. What's d by dx? So let's break this down. D by dx of x squared minus d. I'm going to go on and pull the 2 out. Is that okay? D by dx of y cubed plus 4 times d by dx of y is equal to, what's d by dx of 2? 0. All right. Makes things a little easier, doesn't it? So let's start with this one. What's d by dx of x squared? 2x. Very good. Minus 2. Now, remember our assumption that y is some function of x. Okay? So, if you think of that, y is some function of x, what is d by dx of y cubed? Would be your first response. 3y squared, then chain rule, dy dx. Right? That makes sense? Well, I already had a 2 there, and when you do derivative of that, that's going to give you a 6, because you get a 3 there. So let's just change that 2 to a 6. I could have left the 2 on the inside. That would have made more sense. In fact, let me do that. Let me go back and change that. I thought I was being clever by putting it out there. I wasn't. Okay? Minus 2y cubed. I brought the minus out. And that would be, d by dx of that would be 6y squared, chain rule, dy dx. Okay? Plus, how about this one? 4, what's dy dx is dy dx, right? d by dx of y is dy dx, isn't it? Okay, and that's equal to 0. Okay. Now what can we do? Well, let's first subtract 2x from both sides. And that gives us a minus 6y squared dy dx plus 4 dy dx is equal to minus 2x. Got it? Now, what do you notice about, and what are we looking for? We're looking to find dy dx. Well, there I see 2 of them. So what can we do here? What's the F word? Factor them out. Yeah, let's factor them out. So this is going to be dy dx times, no, on this side, minus 6y squared, right? And over here it's a plus 4, right? Is equal to minus 2x. And what we're looking for is dy dx, so guess what we're going to do? I'm going to change the order. I'm going to divide by 4 minus 6y squared. So your dy dx here, your derivative of y with respect to x, is minus 2x over 4 minus 6y squared. And guess what? It's got a y in there. We still don't have it separated, but this is the derivative of that. And if you know some point on that function, f of x, y is equal to f of x, plug in the x and you figure out what the y is, okay, up there somehow, then you can do anything else you want to do with this. Find the derivative of that spot at that point. So that's called implicit differentiation, where you can't separate the y out. Just go and use the chain rule, okay? And treat y as a function of x, take the derivative of the function, but then you always have a dy dx, y prime. Okay? Now, I'm sorry I cheated. I told you what they're going to tell you now, okay? So let's see. To understand how to find dy dx implicitly, you must realize that the differentiation is taking place with respect to x, okay? That means when you differentiate terms involving x alone, differentiate as normal, like that, what was it, x squared, and it became a 2x, or whatever it was, okay? However, when you differentiate involving y, you must apply the chain rule, okay? First, differentiate with respect to y, but then do dy dx, because that gives you your y as a function of x. Okay? So it's implicit differentiation, follows the chain rule because it uses the chain rule. Okay? So here's one. Okay? The way they have a saying is the variables, are they agreeing or not? Yeah, they're in agreement with each other. Yeah. So what is d by dx of x cubed? 3x squared, okay? That was just not implicit at all, that's explicit. Okay? How about this one? D by dx of y cubed. Three y squared times dy dx. There it is. Okay? Absolutely. Okay? All right? That's implicit differentiation. You first take derivative of the outer function, then the derivative of the inner function, which is your dy dx. Okay? C, which is yes in Spanish, what would that be? Dy dx of x. 1 plus 3 dy dx. Perfect. Perfect. Way to go. And which is, you can then call that dy dx is y prime. 1 plus 3 y prime. Make sense? Can I move on? Okay. Here's the fourth one. D by dx of xy squared. What's that? What rule? Not quite. It's first a product rule. So how does that go? X times. Okay, x times 2y, so it'd be 2xy. You took the derivative of that, got 2y. Those are not the same, so you do chain rule, dy dx. So, okay. So that's what they're doing here. It's going to take them a while. X times derivative of that, so they're taking a while. What's the second part of the product rule? Plus y squared. Just this, because the x dx is 1. Okay? So we still got this to do. So let's us do it. Okay? We got it that far. What do we do next? X. And you're going to have a dy. I'm going to do it dy dx, if that's what you were saying. But I have another part in between or in there somewhere. 2y. Oh, is that what you said? Oh, I thought you said dy. Okay, sorry. All right, sorry. Let me back off and do it, because I like to do the 2y next anyway. Okay, yeah. X times 2y times dy dx, or y prime, or however you want to call it, plus y squared, just y squared, because dy dx, the x dx is 1. So this will be 2xy y prime plus y squared. Okay? Are we getting close to time? Oh, we got some time. Okay. That looks about as simple as I can write it. Okay? I like to pull the coefficient up front, 2xy y prime plus y squared. Okay? Let's see how they did it. Yep. X times 2y dy dx plus y squared times 1 is y squared. That'd be 2xy dy dx plus y squared. That's about as simple as you can write it. Okay. So, I thought we were doing implicit differentiation. Now we're doing implicit differentiation. Okay? Here's the guidelines for this implicit differentiation. Differentiate both sides of the equation with respect to x. If you have an equation there rather than just an expression. Collect all the terms that have the dy dx in them on one side, they say on the left side, and move all the other terms to the right side of the equation. If it doesn't have a dy dx, move it to the right. If it does have a dy dx, move it to the left. Okay. You can separate them any way you want to. Factor out dy dx, which we did, out of the left-hand side, or whichever side you had them in, and then solve for that. Usually by dividing or doing something else to whatever you had left. All right? Is this the one we did, or no, it isn't. So let's find dy dx given that y cubed plus y squared minus 5y minus x squared is equal to -4. Quite an equation, right? I, for one, cannot separate out the y. I cannot write y explicit. So how do I do dy dx? And I don't know if you like it or not, but to me this is what you're doing. D by dx of both sides of the equation. Okay? And what's d by dx of y cubed? 3y squared times dy dx. Good. Plus, what's d by dx of y squared? 2y dy dx. Okay. Minus 5 dy dx, or d by dx of y. Okay. I'll say that whenever I can. Minus 2x. Perfect. Is equal to 0, because the derivative of a constant is 0. Now what? Add 2x to both sides. Separate those with dy dx's from those without dy dx's. And there we've done it. Those go away now. And then what do we do? Factor out your dy dx's. And what does that leave you with? 3y squared plus 2y minus 5. And that's equal to 2x. And now what? Yeah, we're isolating the dy dx. That's what we're looking for. There we have it. We just got to get rid of this. So what do we do? Divide both sides by 3y squared plus 2y minus 5. Divide this by 3y squared minus 2, or plus 2y minus 5. I can't write at all today. Okay, these go away, and there you have it. Dy dx is equal to 2x over 3y squared plus 2y minus 5. Done. Nothing else you can do to simplify, make it any neater, clearer, or anything else. That's it. Now, if you happen to know some value, xy, that's going to always make that true, you can plug that in and find out what the derivative is, and there's a derivative there. Find the tangent line. You can do all the things that we otherwise would have done. So, that's how we did it. Let's see how they did. Can I erase it? Okay. So they're going to start by differentiate both sides of the equation with respect to x. So d by dx of, which actually they're doing exactly what I did, of the left-hand side is equal to d by dx of the right-hand side. The left-hand side, and they did like I did to begin with, break it down into little pieces, d by dx of y cubed plus d by dx of y squared minus d by dx of 5y minus d by dx of x squared is equal to d by dx of minus 4. Which is kind of a long way, but it's fine. If it helps you see it, do it that way. So this is going to be a 3y times the derivative of y. 3y squared times the derivative of y. This is going to be a 2y times the derivative of y. And this is going to be a minus 5 times the derivative of y. And this is just going to be a minus 2x. Because there is no y in there. So the d by dx of x squared is going to be 2x with a minus in front. And d by dx of a constant, negative 4, whatever constant it is going to be 0. Okay? Now, we factor out the we isolate the dy's. So you get all the terms without dy's on one side and all the terms with d by dx of y on the other side. So add 2x to both sides, and then we will factor out the y dx out of everything on the left. That will give us 3y squared plus 2y minus 5. dy dx times that is equal to 2x. Now divide both sides by that factor that does not contain dy dx. And there you have it. And there is your dy dx. Isolated completely. Any questions? All right. Now, what would have been wrong with this graph earlier? In fact, it's part of the problem here. You cannot isolate the y from the x's. Okay? You cannot write it explicitly. Why not? It fails the vertical line test. That's not a function. Y is not a function of x alone, kinda, but they're all intermingled here. Okay, that's part of the problem here. But if you were to graph points on it, and on these, to me, it would seem like it would be easier. Well, nothing would be easy on this problem except verify that when y is equal to 1 and x is equal to 1, we don't even know if that's going to be on the graph. So this would be 1 plus 1 minus 5, so that would be minus 3 minus 1. I'm having problems here, folks. If you put a y equal 1, 1 plus 1 minus 5, be a minus 3 minus 1. Yeah, minus 3 minus 1 is minus 4. That's on the graph. 2, 0, put a 2 here. 0's here. Minus 4 is minus 4. Yeah, that works. 1, 3, that would be a 1, so that's a minus 1. So this would be a negative 27 plus 9 be a minus 18 plus 15. It's minus 3 minus 1 is minus 4. Yeah, that one's on there. Minus 3, 0 looks like it's on 0 minus 3 looks like it's on there. No, it isn't. That's a little below minus 3. Okay. So they didn't put the points there. But yeah, sure enough, those points are on there. So we know that this does plot out some sort of a graph. Okay. So we know, in theory, that actually works. From the graph, you can see y is not a function of x. Even so, the derivative found in example 2 gives a formula for the slope of the tangent line at the point x. The points on the graph that are defined here. The slopes of several points on the graph are shown below the graph. So this one, 2, 0, that certainly looks like it's a negative slope here. Well, what we found, and they're not showing that here. Oh, here it is. If you put in a 2 for x and 0 for y, you have minus 2/5. No, minus 4/5. Okay, yeah. Minus 4/5 is the slope there. If you put a 1 and a 1 here, you're going to have a problem. Okay, because here you'll have 2 over 3 plus 2 is 5 minus 5 is 0. Vertical slope, okay? Undefined, okay? And sure enough, that is undefined. If you put in 1, negative 3, 1 for x, that would be a 2 here, and negative 3 for y, that would be, boy, we did this before, 27, 27 Goodness, my head's not working right. 27 plus or minus 6, minus 5, minus 11 would be a 16. That'd be 2 over 16 or 1/8. Yeah, one up, 1 for every 8 of it. That looks about right. Okay? So sure, we can still use it even though y is not a function of x. We can still use it. Oh goodness, we are out of time, aren't we? Sorry about that. Okay? So we have done basically all right, we're going to start at the top of page 146 next time. There is a slide there. And homework exercises, you can do any of the odds, 5 through 19. They're all at calcchat.com, 5's at calcview.com. I think you can do either 21 or 23. Both are at calcchat, 23's at calcview. And we'll hold off of that and do the slopes of the graph next time. Good deal. Take care. We'll see you Wednesday.
When do you think we'll get this test?
For this chapter?
Yes, sir.
Okay. I think I'll have it ready. I'll try to have it ready for you next time. Okay. Because I wish we had time to do related rates, but those days we missed early in the term, it's going to be hard to make them up. So we're just going to have to skip that related rates. Those are fun problems, but they take a while to do.
Do you know where Miss Anna's office is?
When she's on this campus, I'll show you one of the two that she might be at. I'm going to go on and end this.